Hello, everyone. Thank you for joining us for the Lead and Copper Control with Phosphates webinar. Our presenter today is Darren Scott. I'm the moderator, Ashley Swingle. A few housekeeping items before we get started. We are recording this presentation and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with your question and contact information to follow up directly after the webinar. If you are interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. Do you receive our email blast for upcoming webinars, presentations, trade shows, and technical information on our various solutions? If not, sign up on our website. You can find the Join Our Email list on any landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. We encourage you to connect with our Carus page as well as our team members on LinkedIn, where we are often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from industry experts, and more. And then listed here are links. The first one is our website link, and the second one you can visit to register for upcoming webinars. At this time, I would like to take the opportunity to introduce our speaker, Mr. Darren Scott. Darren has worked for Carus for over 20 years. As the technical marketing specialist, Darren conducts laboratory testing and product demonstrations for Carus's municipal, industrial, and environmental customers and prospective new customers. These product demonstrations include technical training, safety presentations, and installation of safe chemical handling and dosing systems. He is a graduate of Illinois Wesleyan University in Bloomington, Illinois, with a Bachelor of Science degree in Chemistry, ACS certified. Mr. Scott is a member of AWWA, Water Environment Federation, and the American Chemical Society.
Good afternoon, everyone. So our agenda for this webinar is we're going to cover corrosion issues and treatments. We'll talk about the lead and copper rule and the proposed revised lead and copper rule, a brief history of phosphates, how you would go about picking a phosphate product, dosage rates, some case studies from some plants here in the US, and then ways you can go about monitoring your corrosion control success out there in the distribution system. So when we talk about corrosion, we're really talking about four major issues that can cause corrosion in your system. The first is you have both water and different metals that can conduct an electrical current. So that can set up a corrosion cell out there in your distribution system. You have the chemistry of the water that's flowing through your pipe. So what's the pH leaving the plant? What's the pH in the distribution system? Does that change as it interacts with scale and tuberculation? What's the alkalinity hardness of your water going out the door? What's the DIC of the water? Just a host of chemical parameters that you're measuring on a daily basis that can give you some idea of what type of corrosion issues you might have in your system based on that water quality. There is a physical portion of the corrosion factor, and that's really determined based on the type of piping and distribution plumbing that you have out there in the distribution system. Obviously, you look at the newspaper or turn on the news, and there's lots of articles recently about removing lead service lines out there from the distribution systems. So one of the things you hear a lot about is how many lead service lines do communities have, how fast are they going to remove them, and that just applies to the whole distribution system. You know, what type of distribution piping do you have? Is it cast iron? Is it ductile iron? Is it asbestos cement? What kind of service lines do you have? Copper, lead? What kind of plumbing do consumers have in their home? So just that physical makeup of the system can determine what types of corrosion you might see out there in the distribution system. Finally, there is a biological portion to corrosion. So one of the things you do is you maintain a free chlorine or a monochloramine residual out in your distribution system. And the idea is you maintain that residual to keep bacteria under control so that you don't get bacteria growing on the inside of the pipe and causing bacterial influenced corrosion. You can have iron bacteria, sulfide bacteria that can cause a whole host of problems if they get out there in the distribution system and start growing. And so you do want to make sure that you're maintaining that residual of your disinfectant in order to keep them from growing out there in the distribution system and influencing corrosion. So really it's those four components together and how each one interacts differently based on the materials in your system, your water chemistry, to determine what type of corrosion issues you might see in your system. So when we talk about corrosion in your distribution system, there's a lot of different things that can go into that. If you have a corrosion issue, like you can see here with the distribution main that's awfully corroded in the picture, you can have tuberculation deposits. As that pipe corrodes, you get that iron oxide calcium carbonate scale, and that pipe is restricted from where it was originally very smooth and much larger when it was initially put in the ground. As that pipe gets restricted, it costs you more money to pump water through that pipe out there in the distribution system because you're restricting that pipe. One of the things engineers will do is when they're designing a distribution system, they size the pipe in the distribution system based on how many customers and how far they need to transport that water. So as you restrict that pipe, that fights against all the design work that they did up front of carrying the water out to your customers. Now the fire department is typically going out and they're flushing fire hydrants in your community, and they're doing that to determine can they get sufficient water at a sufficient pressure out of a fire hydrant to fight a fire if there's one in the neighborhood. They have to report those numbers in different communities, and that can actually set the insurance rating for homeowners in that community if they have impacted water mains at a higher rate. Obviously, if you have a lot of scale and tuberculation in the system, that's a lot of stuff for your chlorine or monochloramine residual to interact with, and you could see a loss of disinfectant residual as it interacts with that scale and tuberculation. So you'll see your residual drop off and you might feed more at the plant, or you might feed a booster dose out in the distribution system to boost your disinfectant demand. Obviously, if you've lost your disinfectant demand, that's a chance for bacteria to grow. You could get a bacteria hit. You might have to issue a boil water notice out in the system. So obviously those are things you want to avoid. With scale and tuberculation, like you see in that picture, obviously some of it can break free, cause discolored or rusty colored water to end up in the customer's home. And you'll have to respond to that complaint. So you might go pull samples from that neighborhood. You'll probably go flush fire hydrants in that neighborhood to flush the bad water out and get fresh, clean water into that neighborhood. So you might have to do that more often in a system with a lot of corrosion. You might flush, spot flush once a month or every several months to keep it under control. If things get really bad in the distribution system, obviously this scale and tuberculation is impacting the pipe wall. You can get a leak or a main break, and obviously now you've got to go respond, dig up the pipe, and replace a portion of it or patch it as best you can. Here in the Midwest, as we're getting into the colder weather and the temperature change, it can speed up some of those leaks and main breaks as the ground freezes and thaws out there. Obviously, leaks and main breaks don't happen in the nice weather where it's 80 degrees outside and sunny. They happen in cold weather, rainy, snow weather, and not during normal hours, so you have to respond to them. The whole idea, though, with corrosion is you can do everything right at your water treatment plant, whether it's groundwater or surface water. That water can look great, taste great, meet all the regulations for the US EPA and your state regulators, and then you send it out the door, and as it passes through the distribution piping, it picks up colors and tastes and doesn't look the same and doesn't meet the same regulations at the customer's house. Obviously, as soon as the customer turns on the tap and see discolored water or the water tastes off, they're going to call somebody, whether it's you at the plant, somebody on their city council, their mayor, and complain that the water is not exactly like they expect it to be. If you don't respond to those complaints, obviously it can get very bad. They can go to the local news media, and you can be in the paper or on TV about not responding to customer complaints. So that's something you want to avoid. Obviously, if you're failing to meet regulations, then you can have both the state regulators taking action to tell you what you're going to do in the future to treat your water going out the door. So as far as regulations, by far the largest one that you have to comply with is the lead and copper rule. So the original lead and copper rule went back to 1991 when it was established. In 2007, there were some short-term revisions published to the lead and copper rule that updated some of the language that you would use. In 2014, Flint, Michigan hit the national news with their issues with lead in the distribution system. In 2015, the EPA had some white paper recommendations. And then at the beginning of 2021, the lead and copper revised rule was published in the Federal Register. Now, there's been some date changes on the proposed lead and copper revised rule. Right now, the rule is scheduled to go in effect on December 16th of 2021. And the compliance date has been moved back from the beginning of 2024 to October 16th of 2024. Now, twice this year, this regulation has shifted dates. So it is still possible that they could make another shift in both the effective date and the compliance date. But right now, this is where the final rule stands for the revised rule. So from compliance in 2021 to 2024, you're still going to comply with the original lead and copper rule from 1991. That set the lead action level at 15 parts per billion, and it set the copper action level at 1.3 milligrams per liter. In the original 1991 rule, the maximum contaminant level goal for lead was 0. So we know even back in 1991, the goal was to try to get to 0 parts per billion of lead in water. And the copper action level with the goal of being 1.3 were the same. So we didn't think of copper as having as serious of health effect as lead. Now, the lead and copper rule was established because lead has delays in physical and mental development of children. It also can cause kidney problems and high blood pressure in adults. Copper has stomach, liver, and kidney problems. Lead is the one that gets most of the focus because we've removed lead from gasoline, we removed lead paint from homes and toys because of the impact it could have on children. So we do want to get the lead out for children because they could consume it by drinking the water. The current lead and copper rule establishes that it's an action level. What that means is it's the 90th percentile value to determine compliance. So you collect the number of samples for your system based on system size. You take them from lowest to highest, and you take the 90th percentile number, and that determines your compliance with the regulation. What that means is you are allowed under the current lead and copper rule to have 10% of your samples above those action levels. So you can have 10% above 15 parts per billion for lead, and you can have 10% above the 1.3 copper action level. Now, like I said, the monitoring is based on the size of your distribution system, and you're targeted mostly toward high-risk sites, lead service lines, under the 1991 lead and copper rule. The initial frequency for this rule was every 6 months. If you consistently met the action level, you could go to once a year. If you consistently met the action level there, you'd go to half the number of samples, and then finally you'd be on a schedule of once every 3 years and half the number of samples as long as you stayed in compliance with the action level. So there was a benefit of staying in compliance because you had a lot less testing to do in the system. The lead and copper rule does establish that it's a first draw, which means it should be 1 liter of water from a cold water tap that has not been used for at least 6 hours. The current regulation has no upper limit on stagnation. So if it's 8 hours, 24 hours, 48 hours, it's still a valid sample once you get past 6 hours of stagnation time. Now in 2016, the US EPA had some recommendations which are going to be in the new revised rule, but they recommended that you had no pre-flush. So no flushing the tap the night before you're going to pull the sample the following morning. They asked to use wide mouth sample bottles, and the new proposed rule talks about those as well. The idea being that you can pull a sample at the full flow velocity out of your faucet. So open the faucet fully so you're flushing at the highest velocity out of that tap. And they also recommended don't remove the faucet aerators or their screens because they could trap lead particulate, and you want to operate them normally how a customer would as well. If you had a violation of the 1991 lead and copper rule, you were required to do distribution of public education. You're required to go back to the beginning of monitoring your consumer taps. So you pull them every 6 months at the full number of customer taps you're required. You would have to develop and submit a corrosion control plan. And the options in the 1991 rule are pH, alkalinity, hardness, or some type of corrosion inhibitor. So you have multiple options to pick. Also, if you continue to be out of compliance, you could do lead service line replacement, and it was supposed to be a minimum of 7% per year, but there were options to test out of having to replace that many service lines each year. Now, the proposed lead and copper rule that's out there in the Federal Register has a lot of changes to that 1991 rule. Now, it doesn't go into compliance date until 2024, so there's going to be 3 years for you to get into compliance. It does not change the copper action level, but it does require now that you're going to have to develop a lead service line inventory. Some states are already ahead of the game and have had this requirement for several years, but you're going to have an inventory of how many lead service lines, how many unknowns, and what other types of materials that you have out there in your distribution system. And this is for both the public and the private side. So you need to know both sides of the service line. You're going to have to do lead service line replacement updates. So what they want to do is that you have a plan for doing lead service line replacement. You can no longer do partial lead service line replacements. They have to be a full replacement. And then after that replacement in the proposed rule, you'll have to provide the customer filters so that they can filter the water for several months after you've replaced that lead service line, so they can filter out any high lead levels they would have after that change. In addition, lead and copper sampling has to be done at 20% of public and private schools in your community, and they also have to be done at licensed child care facilities. So there'll be some additional sampling that you'll have to do and work with those customers to pull them. One of the things the rule now lays out is that within 24 hours of knowing that you've had an action level violation, you have to notify the public. That can be done in several ways, but basically, as soon as you know you have a violation, you have to let the public know that you've had it. This would be reverse 911 calls. It could be radio and TV ads. It could be on the website for the city. Basically, multiple ways to get the information out to the consumer that you've had a violation of the rule, so they can take action so they're not exposed to high lead and copper levels. Now, the lead action level does not change. It stays at 15 parts per billion, but several things are going to make your lead levels rise in the system. In the new regulation, every single sample that you pull must come from a home with a lead service line if you have enough samples to come from homes with lead service lines. So everything will now be targeted toward the highest risk sites. It will also have a trigger level for lead of 10 parts per billion. So if you're between 10 and 15, what it will do is you'll trigger that you have to do extra testing in your system. So if you're above the trigger level, your sampling will be every year. You'll have to do a corrosion control study or a reoptimization study. You'll have to replace lead service lines, and it's mandatory according to your plan for a minimum of 2 years while you're above that trigger level. Now, small systems do have some other options, but for larger systems, what's going to happen is you're going to be replacing lead service lines once you've had a trigger level violation for 2 years, based on what you've submitted to the state for how many you're going to replace per year. The other part of the lead sampling is you're going to have first a first draw and a 5th liter draw sample. So there'll be 2 samples that you pull for lead compliance, whereas the copper will still stay as only the first draw sample. Now, as part of this update, your corrosion control studies will have to be targeted toward lead service line loops that are harvested if you have lead service lines in your system. Now, this is also based on system size. So larger systems will have to do this. Smaller systems will have some alternative criteria. You can't rule out phosphate or pH adjustment based on other water quality issues that they may cause in your system. So if those are one of the 2 best options you have, you're going to have to use them. Part of this corrosion control study update also eliminates alkalinity hardness adjustment as an acceptable corrosion control technique. So you'll have to switch to either pH adjustment, a phosphate, or some type of silicate corrosion inhibitor in order to have a corrosion control product. So I kind of talked about these just now. So there's multiple ways for you to reduce corrosion in your system. Probably by far the most common is pH adjustment. Raise the pH of the water up so the water is less corrosive and not acidic. There were passivation techniques that you can still use. They do reduce the corrosivity of the water, and this can be alkalinity adjustment or calcium adjustment by adding something like lime or sodium carbonate to the water. They're currently acceptable techniques, but in the proposed long-term rule for lead and copper that's revised, they'll go away as one of the acceptable corrosion control techniques. Chemical inhibitors, which include phosphate products and silicates, are currently acceptable, and they will be in the new rule. You can also do some other things to your water quality, like reduce your DIC, so do it through air stripping, do lime softening to change the bulk water quality, some type of ion exchange. So there are some other things you can do in your system for corrosion. And finally, the last one is you can do some type of physical protection. You might reline or put a sacrificial anode in a tank or a tower to protect it. We've seen systems that have PIG distribution mains to remove scale and tuberculation and then reline them to provide protection for small parts of the system. So there are a lot of options that you can pick. Specifically, we're going to talk about phosphate products. Phosphates were first used in drinking water treatment all the way back in 1887. In the 1930s, sodium hexametaphosphate, SHEMP for short, was used a lot for calcium carbonate scale control in industrial applications. Anywhere where you had a heat exchanger where you get a lot of calcium carbonate scale buildup, they'd use sodium hex to prevent that scaling so they could run the equipment longer. In the 1970s, zinc orthophosphates were introduced for treatment of low hardness, aggressive water supplies. So if you had red water complaints and a very soft water, so less than 20 hardness, less than 20 alkalinity, that would cause a lot of red water complaints. So they started to use zinc orthos to provide corrosion control. Obviously, we talked a lot about the 1991 lead and copper rule, but that made phosphate use in a lot of corrosion control techniques explode because now you had a regulation that said you have to meet a lead and copper level at the consumer's home. So corrosion control became an imperative thing to do in your system. Now, when we talk about phosphates in drinking water treatment, we're really talking about two applications. We're talking about corrosion control, specifically for lead and copper, and we're talking about sequestration, which would be tying up iron and manganese for color control or tying up calcium carbonate for scale control. In the US, approximately 55% of all water utilities use some type of phosphate product for either corrosion control or sequestration. In the US, AWARF says that there's roughly $200 million spent annually on phosphate products. In that study, they said there was a $4 billion savings in investment, or a 20-fold return on investment. What the AWARF study said is we are spending $200 million on chemicals and treatment for corrosion control, but all the things that you get out of that corrosion control treatment can save a water plant a lot of money. Obviously, if you've got to replace distribution mains, there's a large cost to do that. If you've got to respond by flushing water hydrants out there in the system, that's water you paid to treat at the plant, but now you're dumping it to the ground and not recouping that cost. Any water samples you collect and have to send to a lab for testing for a consumer, there's all these costs that add up slowly over time. Costs of phosphates range anywhere from 30 cents to $2 a pound, and typically somewhere between 1 cent to 10 cents per 1,000 gallons of water treated. So there can be a variable cost, and it really depends on what your main application is. There continues to be desktop corrosion control studies done by the US EPA, by AWARF and engineering firms, determine what are the best products you can use in your system as far as providing both corrosion control and sequestering. Now, one of the questions that comes up a lot at Carus is the first time a customer is going to use a phosphate product, they typically say, we're going to get customers that ask us, well, you're adding a chemical to the water and all chemicals are bad for us. Well, phosphates are something that people and consumers come in contact with on a daily basis. They're a food additive. So they're a leavening agent in donuts and bread. So people that consume donuts and bread on a daily basis are getting some phosphate content. They're a dairy emulsifier in cheese. So there's phosphate content there if they eat cheese on their burger or on their pizza. They're also in the can of Coke or Pepsi that you drink. Those typically contain phosphoric acid as one of the top 3 ingredients on the list. Levels might be somewhere between 1,000 and 10,000 parts per million in a can of Coke, whereas we typically feed it 1 to 3 milligrams per liter of parts per million in drinking water, so much lower dosage. Phosphates are also in toothpaste as plaque inhibitors and whitening agents. So if you turn over your toothpaste tube, you'll see a lot of different phosphate compounds listed. They're also used in some drug manufacture. By far, the largest use of phosphates is in fertilizers. 80% of the global demand is in fertilizing fields out there in the US and worldwide. They're also sometimes in cleaners and detergents. So if you look at your box of Tide or your dishwasher detergent, they might have phosphate compounds listed. A lot of them have slowly been replaced over time with other components that aren't phosphate based, but you might still see them in some of those detergents and cleaners. So phosphate use is all around us. It's in things we consume. So adding it to drinking water at much lower levels than what we consume in food shouldn't be a concern for anyone. Now, when we talk about improving finished water quality, we're talking about these kind of 3 main applications. We're talking about preventing calcium carbonate scale, where it scales up the pipe or it causes hard water spots on your dishes. We're talking about preventing iron and manganese precipitation in your distribution system, so you don't get tea-colored water in the case of manganese or red rusty water in the case of iron dropping out. And then finally, lead and copper corrosion in that service line running to the consumer's home or in the plumbing in the consumer's home. Now, typically when we talk about corrosion control for lead and copper, we're talking about systems that are having issues with exceeding the action levels for the current rule of 15 parts per billion for lead and 1.3 milligrams per liter for copper. If you're below 40 hardness, below 40 alkalinity, that kind of soft water typically will have a lot of issues with meeting lead and copper compliance. Now, you obviously can have issues in even hard waters with lead and copper compliance, but those issues pick up steam when you don't have a lot of other content in the water in these soft surface waters. In the case of iron and manganese precipitation, this is typically going to be a groundwater plant that's not doing any type of treatment for removal. So they're going to pump the groundwater out the door. They might treat it with just chlorine, fluoride, and a phosphate product, and then it goes out the door without filtration. In that case, you need to tie the iron and manganese up so you don't get discolored water. In this case, the EPA has what they call secondary maximum contaminant levels. For iron, that level is 0.3 milligrams per liter. For manganese, that's 0.05. What the EPA is saying is they're a secondary effect because they're not considered health effects at this point in time. They're considered aesthetic effects. You'll have staining on laundry and fixtures. You'll have discolored water. So you'll generate a lot of customer complaints if you're above that iron and manganese level. So if you sequester, the water will look clear, but that iron and manganese will be there, it just won't have precipitated out a solution. In the case of calcium carbonate scale control, once you start to get above 100 hardness and then varying pH levels that get higher, you can start to see some scaling issues. Much more likely at 300 or 400 hardness with a higher pH to see scaling issues, but they can scale a pipe, they could scale over your filters in your water treatment plant, or they could cause scaling in fixtures in schools and water fountains and or in your home. So when we talk about phosphate products, there's 2 distinct classes. There's orthophosphate, which is 1 PO4 unit by itself, and there's polyphosphate, also sometimes referred to as a condensed phosphate, which contains several PO4 units chained together. In the case of orthophosphate, that 1 PO4 unit, this is what we typically think of for corrosion control. In the case of a polyphosphate, it may be as simple as 2 or 3 or 4 PO4 units in a straight chain. These are typically very good at sequestering iron and manganese. Or it could be what's called a metaphosphate, which is a ring structure, and typically it'll be somewhere between 5 and 15, maybe 20 PO4 units in a ring structure. Much better at calcium carbonate threshold treatment. Can do a little bit of iron and manganese sequestering, but more toward the calcium carbonate side of things. Now, there's been a ton of research done over the years. We know phosphates work in 2 ways depending on the product you're using. Phosphates, in the case of orthophosphates, will form an anodic film. So they'll form a barrier between the pipe wall itself and the wad to prevent metal release. In the case of a polyphosphate, it's a cathodic inhibitor. It provides a barrier so that oxygen can't interact with that metal. In the case of iron and manganese in solution, it'll prevent the oxygen from oxidizing it, where it would precipitate out, but it can also prevent dissolved oxygen from attacking the metal of the pipe wall and causing some corrosion. What we do know is these compounds are very insoluble, phosphate salts that form on the surface, and we're still learning more today. There's still research continuing to go on at AWARF to look at different levels, different treatment complexes out there in the system to determine what would be the best product for each site. So when we talk about corrosion inhibitors, if you're using something that's an anodic film former, it would be the orthophosphate portion. If you're using a zinc ortho, it would be the orthophosphate portion of the zinc ortho. And a silicate would also be an anodic film former. On the cathodic side, things like calcium carbonate, polyphosphate, or the zinc portion of a zinc orthophosphate would be cathodic inhibitors. So you can have protection on both the negative and positive side in a system if you're using a product that combines multiples of these. So if you've got a zinc ortho, you have both sides. If you have an ortho poly blend, you have both sides of this corrosion cell. Now, there's been a ton of research done out there. We know that the orthophosphate precipitates with the 2+ valence states, or whether that be calcium, magnesium, but it can also bond directly with the lead and copper plumbing out there in the system. Michael Schock did a lot of the original work showing the formation of the insoluble film that forms on the inside of the pipe. We know that the phosphate can bond directly with the iron to form linkages to help reduce the amount of corrosion you see. We know that it doesn't take a whole lot with iron distribution piping. As little as half a part can reduce the amount of iron that we release from the pipe by 2/3. So you get a really big benefit in that first part dosage with orthophosphate as far as iron release from your distribution piping. Overall, though, all the research shows that when you're feeding an orthophosphate product, you're typically going to reduce the corrosion rates in your system, which means less iron release and also less lead and copper being released into the finished drinking water that the consumer would drink. Now, you can feed a straight orthophosphate, but you could also feed a zinc orthophosphate that combines both the zinc and an ortho. Now, these products, like orthos and zinc orthos, do no sequestering. All they can do is do that anodic film formation to protect the pipe. They're very quick to film forms on the pipe. Passivation can take place in weeks. A lot of times people that were on zinc orthos would talk about having a minimum of 30 days on a higher dosage to help form that film in the system, and then they would back off to their maintenance dose. Sometimes systems might do 90 days or 6 months at that higher dosage and then back off. The whole idea is get that film established in the system, lower those corrosion rates, and then back off to a maintenance dose. Dosages would range anywhere from as little as 1/10 of a part of zinc up to 1/2 a part of zinc. Some systems did feed a little bit higher. And then orthophosphate content anywhere from a minimum of 1/2 a part, sometimes up to as high as 3 milligrams per liter as orthophosphate. Now, one concern with feeding a zinc orthophosphate product is you're adding zinc to the drinking water system, so that zinc will end up at the wastewater plant, and some wastewater plants have a zinc loading limit on their discharge. So if they're close to that loading limit and you add a zinc ortho in that type of system, you could throw the wastewater plant over their zinc discharge permit. And so there might need to be a discussion between you and the wastewater plant How close are you to your loading limit? Can I add a zinc if it's the best product? Because it's not the easiest thing to remove the zinc at the wastewater plant. So you do want to have that discussion before you institute a zinc ortho. Now, when we talk about optimal levels, we know that typically you're going to be at about 1 milligram per liter as orthophosphate to reduce lead and copper solubility, ideally in that range of 7 to 9 for your treated water. A lot of the research showed that there wasn't much above 3 milligrams per liter, that you wouldn't get much more benefit, although some of the current research is showing that maybe some levels will need to be as high as 4 or 5 milligrams per liter to reduce lead numbers in the system. The current EPA guidance document talks about sampling and feeding an orthophosphate somewhere between 1 and 3 milligrams per liter. What Carus has seen over the years is a lot of systems on orthophosphates only are somewhere between 1 and 2 milligrams per liter as their target dosage in the distribution system. So they fit that lower end of the spectrum. Now this might change with the new lead and copper rule and the sampling from lead service lines. You might see a shift more toward 2 or 3 milligrams per liter to lower those lead numbers even farther in the system because of the new trigger level. Our first case study here is a system that had copper corrosion. Their 90th percentile levels were 1.52, so just above the 1.3. They were a surface water plant, 5 MGD, and they were treating in the surface water plant, so they were removing the iron and manganese that you saw there. pH was on the low side at 7.1, but you can see their DIC was very high at 57, so that water is very conductive. What they chose was a zinc orthophosphate, and it was a 1:3 ratio. So they were targeting 1 part as orthophosphate and roughly 0.33 as zinc in the system. They started feeding that system, and over the course of a year, the copper TAC levels decreased 70% from their first draw samples. So they dropped from 1.52 down to 0.46 milligrams per liter. So well below the 1.3 regulation with this treatment. The levels remained low with respect to the high DIC and dissolved oxygen in the system. So this was providing continued corrosion control at this target level of 1 milligram per liter for copper. You might also have issues with sequestering besides corrosion control. So in this case, you might want to feed a polyphosphate for sequestering of metal content. What you're trying to prevent is either dissolved oxygen or chlorine from oxidizing the metal and precipitating it out of solution in the case of iron and manganese. The idea being you have clean, clear water, whereas if you had iron that would precipitate, you'll have rusty orange water. If you had manganese in the water, you would get black or brown discolored water in the system. Now, in the case of calcium carbonate sequestering, we're really talking not about true sequestering, we're talking about threshold treatment. What we're doing is just have enough polyphosphate in the system to prevent those crystals from forming large enough so you get a lot of scaling. So one of the things you would see with the sequestering dosage based on the amount of poly in your system is you'll feed a much higher level for iron and manganese sequestering than you would for calcium carbonate scale control. So the dosages will be quite different depending on what you're trying to accomplish, and much on the higher side for iron and manganese. Now, same thing here. There's been a ton of studies done over the years showing how polyphosphates work. They can sequester metals depending on the water chemistry. So how much iron, how much manganese, what else is in the water to sequester. We know that they will tie up iron and manganese to reduce the color and turbidity, so you won't have discolored water out in the system. There's been research that shows that polyphosphates, along with proper disinfection, whether it be free chlorine or monochloramine, will reduce biofilm counts, so it'll help break up biofilms out there in the system. And polyphosphates are also used in well cleaning to break up biofilms along with disinfection if somebody needs to clean their well every several years because they've got a lot of biofilm built up in their well casing. Now, one thing we also know is that all polyphosphates do revert to orthophosphate over time, so that polyphosphate chain does break down to ortho. So if you're feeding a poly-ortho blend or a poly, your orthophosphate content will come up as that water ages in the system. What that means is two things. for your neat product, if you have a polyphosphate in your blend, that means you have a shelf life of roughly about a year, where you'd like to turn the product over and get fresh product every year at your plant. It also means when you're trying to sequester in the system, we want to try to turn that water over as quickly as possible for sequestering iron and manganese, and we'd love to stay within a water age of 3 to 5 days for sequestering. As you start to push out to 7 or 10 days of sequestering, some of that iron and manganese may still precipitate out, and you may still get some discolored water at dead end lines or far points of the distribution system. So if you can move that water quickly through the system with sequestering, you won't see those issues. Whereas if the water age gets much longer, you might have issues. One of the things to keep track when you're feeding a polyphosphate product is when you go out and do flushing, keep track of how long it takes you to flush a fire hydrant until the water clears up. If you're having to flush for 10 minutes, 15 or 30 minutes until the water clears up, that means you've got a lot of scaling tuberculation out there in the system. Ideally, what should happen is when you flush a hydrant, there'll be some water between the distribution main and the fire hydrant. And so you might see, 30 seconds, a minute of discolored water, and then pretty quickly, the water clears up and you're flushing clean water out of the hydrant. If you have to flush for a really long time with discolored water, that's a pretty good hallmark that you've got a lot of scale and tuberculation and corrosion issues going on out in your system. It's always a good idea for a system to have a flushing program, ideally being unidirectional, so you flush at the plant and go outwards in the system. And ideally, if you could do it twice a year, that would be the best, just to move water quality through the system and change that water over. Now, one of the things I talked about a little earlier was the schematic of biofilm removal. So what's happening here is that biofilm grows on the pipe wall, and that protects itself with a slime layer so that the chlorine or monochloramine can't really disinfect that slime layer. So it kind of stays in equilibrium on the pipe and with the water itself. The polyphosphate can come in, it can grab onto a positive metal ion like iron or manganese is trapped in the biofilm or calcium. As it takes that metal out of the biofilm itself, that punches a hole in the biofilm, which now allows the free chlorine or monochloramine to get into the biofilm. And then slowly over time, you'll break that biofilm up. And with proper disinfection, you can remove it from the system. The idea here is slow and steady wins the race with your dosage. So in a distribution system, you would just feed your normal dosage for sequestering along with your normal dosages for chlorine and monochloramine, and you'll get some of this cleanup of the system slowly over time. In the case of a well cleaning, because they're trying to clean that well up immediately and very quickly, they might dose 1,000 parts of a polyphosphate product to break up that biofilm and kind of break it up. And then they'll come back with a dosage of 1,000 parts of free chlorine to disinfect that pipe and then flush all that to waste and then test the well to see what the bacteria count is after they've done this cleaning. They'll also look for flow rate improvements as well. So sometimes they might do a mechanical cleaning and then this chemical cleaning to help break up this biofilm and remove it in a well application. So we've talked about polyphosphates, we've talked about orthophosphates. So you can blend the two together, obviously, to get a little bit of both benefits. So you can do sequestration, you can do a little bit of corrosion control, you can help prevent or remove some scale deposits depending on how much you feel, and then you might break up some of those biofilms as well. When we're feeding a polyortho blend, we're going to look at two things. We're going to look at how much orthophosphate residual you have in the system. That level will go up if you're more focused on corrosion control for lead and copper. So you might feed 1 or 2 or even 3 parts as an ortho in the blend for corrosion control. And then your total phosphate dosage is the combination of ortho and poly together. So the difference between total and ortho will be your polyphosphate number. That will be based on how much iron and manganese and how much calcium carbonate you're looking to sequester or tie up in the system. So that will shift as well. If you don't have a lot of stuff to sequester, your ortho and total number will be much closer together because you don't have much polyphosphate in the system. This will be based on the product and your water quality. determine what the levels of ortho in total will be in your system. One of the ways to pick a product would be to do a coupon loop. In this case, a system with a water quality in the mid-7s, no iron and manganese after treatment as a surface water plant, hardness of 140, alkalinity of 110. They looked at a couple different treatment ranges. So they treated at half a part and 1 part to determine if a low dosage would work. And then they came back and tested side by side multiple products at the 1 milligram per liter dosage as total phosphate. In this case, looking at their corrosion rate, they used phosphoric acid, so a straight orthophosphate, and they used a 30 poly 70 ortho blend, also at 1 part as total phosphate. What you can see from the coupon data was with phosphoric acid, the corrosion rate was roughly close to the same with the phosphoric acid. What that would tell you is you probably would have to increase the dosage to 2 or 3 milligrams per liter with phosphoric acid in this situation. The blend did show a reduction in the corrosion rate for lead. You look at the copper coupon, phosphoric acid lowered the corrosion rate, and it was the best product at 1 milligram per liter. The blend had a slightly worse corrosion rate for copper, although it still did reduce the corrosion rate in the water. Finally, on the mild steel coupon, phosphoric acid lowered the rate quite a bit. The blend was slightly better. So what you can see is you've got some different results depending on specifically which coupon you would be focused on. But just keep in mind, these were both targeted at 1 milligram per liter as total phosphate. So with the phosphoric acid, that would have been 1 part as ortho. With the 30-70 blend, it would have been 0.7 as ortho, so slightly below 1 milligram per liter, because you would have had 0.3 as poly. If you look at all 3 of the coupons, the blend was slightly better in this situation because it had a much lower lead corrosion rate. It also had a mild steel corrosion rate that was lower. Copper was a little higher. So if that would have been your main focus, you probably would have picked the orthophosphate for the copper corrosion. One of the reasons for this, we think, is the blend had a little bit better protection because you had both anodic film formation and some cathodic protection from the polyphosphate portion. A case study here, plant operation was a groundwater filter plant, had 5 wells blended together. They did have iron removal, 1.2 mgd. Water quality, we were in the mid-7s. Not much iron going out the door, 0.04 to 0.01. So the iron removal was working effectively. But the hardness was really high, depending on which wells were operating, anywhere from 290 to 320 milligrams per liter. And the alkalinity was pretty high at 250. They were experiencing lead levels above 50 parts per billion at some sample sites in the community, and their 90th percentile action level for lead was at 23 parts per billion, so above the 15 parts per billion. So their treatment approach was they were going to use a 15 poly / 85 ortho product. So they wanted some sequestering for the high hardness, but they wanted a high level of orthophosphate in the system to get those lead levels down. So they targeted a total dosage of 3.2 as total. They also did coupons at the same time they did first draw sampling in the system. The coupons showed a reduction of 52%. So you're showing a reduction theoretically that would tie to what the distribution system would see. Now they kept doing these coupons every 90 days to keep collecting that data while they were also feeding to the system. When they went and pulled first draw samples, they noticed that they had roughly a 90% reduction in first draw samples at consumers' homes. So if you look at the data, before they added the phosphate treatment, their highest level of lead from a sample for compliance was 50 parts per billion, and that 90th percentile was 23. Post adding the phosphate at that dosage, 1 year down the road, their highest sample went from 50 to 18 parts per billion, and their highest 90th percentile sample dropped to 2 parts per billion. So there's your 90% reduction from 23 to 2. Year 2 of feeding the product, their highest sample they got on a first draw was 12 parts per billion, and the 90th percentile stayed at 2 parts per billion. So you can see that drop in lead sampling numbers out there in the system at that high dosage. So how do you specifically pick a phosphate product? What you want to do is look at the water quality leaving the plant, and then what's your water quality do as it passes through the distribution system? Does some of those water quality parameters change? Do you pick up lead and copper numbers? Do you pick up iron and manganese from the system, from scale and tuberculation? What's your water quality doing in the system? Also, what issues are you having? Are you getting occasional dirty water complaints from customers? So maybe you want to try to eliminate some of that. Is it strictly you've got a lead and copper issue and you want to get compliance with the regulation? So is that your main focus? So having that discussion of what issues you're trying to fix with this product. And then establishing what are your goals. So what are you trying to target? How low do you want to go on your lead and copper numbers? Do you just want to get into compliance? Are you focused on a lower number, looking at the future regulation? So you might target a higher dosage at that case. So you want to have all this discussion up front when you pick a product and a dosage. Ideally, what you're going to look at, what's the hardness / alkalinity of the water? How much iron and manganese do you have in the finished water? And if you have treatment for removal and filtration, what's that actual number going out the door to the distribution system? So keep in mind, if you're a groundwater plant and you're doing sequestering, if you're above 0.3 for iron and above 0.05 for manganese, you're definitely going to have to use some polyphosphate for sequestering. But if you're a groundwater or a surface water plant that has oxidation and then filtration removal, if you're well below those numbers, you might not require much polyphosphate for iron and manganese sequestering. Do you have background orthophosphate in your water? In the case of a groundwater, you might have a couple tenths of a part of background ortho. So your dosage is going to be in addition to that background ortho. So if you have 2/10 of a part of background ortho and your target dosage is 1, you'll really want to see 1.2 out in the distribution system. So in addition to what's in the background. What's the pH of your water going out the door? Ortho poly blends work best between pH 6 and 9. Ideally, though, we'd love to be in the mid-7s to be optimal. In the case of a zinc ortho, you really need to be in that mid-7 for them to work the best. So your pH range will matter. It also matters depending on if you're focused on lead or copper, because as you increase pH, copper corrosion rates go down. So you might target an 8.5 to a 9 with a copper corrosion along with a phosphate product and see better results than you would at 7.5. So you do want to consider that as well. Now there are a host of other parameters. You can look at chloride to sulfate ratio. You can look at dissolved inorganic carbonate levels in your system. So based on your system, you want to look at other parameters as well to determine what could be causing your corrosion. What does this mean? Product-wise, it means if you've got no iron and manganese, you've got no hardness, you're typically going to be an ortho or a zinc orthophosphate product. If you have a lot of iron and manganese, or you've got a really high hardness, or say you're a lime softening plant, you might use a straight polyphosphate for sequestering to tie up that mineral content. And this is especially true if you don't have any issues with like lead and copper in your system, you might use a polyphosphate. In the middle, you'll use a blended phosphate, and it's really going to depend on how much iron and manganese hardness you need to sequester and what level of orthophosphate you need for corrosion control. So you'll pick that blend and how much you feed based on those water quality parameters. So this kind of gives you an idea of where a product might fit in based on some water quality parameters, but it can shift based on other factors that you need to comply with. Now, one of the questions we get asked at Carus a lot is, when you inject a phosphate, does it matter where you add it? Well, typically, if you're going to add a phosphate product, what you're really concerned with is if you're sequestering for iron and manganese. In the case of sequestering for iron and manganese, the phosphate needs to be injected prior to your chlorination because chlorine will oxidize the iron and manganese and precipitate it out of solution. So in that case, the phosphate would go first. In a groundwater or surface water plant that has oxidation and filtration, you'll then typically add the phosphate after filtration going to your clear well or going to your distribution system. You don't have to add it prior to the chlorine because you removed that iron and manganese. Phosphate products are typically added neat. You can use carry water or dilute if you need to, but phosphate products blend in pretty well. You can pick whatever type of pipe pump you want, peristaltic, membranes, diaphragms, flow pace it, SCADA control it. You have lots of options. And there's material compatibility information that you can request from Carus to pick the right materials for your pumps and your piping. Now, some things to keep in mind. The state regulator is probably going to ask you these as well, but do you have a calibration of your metering pump in mils per minute or gallons per hour? And then also, do you know how much phosphate product you fed on a daily basis? So do you have a weigh scale or a level indicator on your day tank so we can determine how much product you fed, plus with how much water you've treated, we can calculate the dosage of phosphate that you're feeding to the system. Now, once you've dosed the phosphate into the system and you have those measurements of how much product you fed and water you've treated, you can also measure to make sure that you're seeing that in the system once you've added it. There's a US EPA approved method for phosphate. It measures orthophosphate as PO4, and it's a really simple test. You add the powder pillow, you mix the sample, you wait 2 minutes, and then you can read this either on a color wheel that they still produce, or it's better if you read it on a spec so you can get a true reading of the number, not based on your eyesight. The darker the blue color, the higher the orthophosphate content. So just by looking at color, hence the reason why you can still use color wheels, you can determine what the level is, but you can also get a digital readout of what that color is as well. Ideally, you measure a phosphate product at a couple points in the distribution system. Test at the water plant itself, test out in the distribution system, and then maybe test at a far point. What you're going to try to target is your residual level should be pretty consistent once you've established that anodic film in the system. They should be pretty consistent throughout the distribution system. Now, if you are feeding an ortho poly blend, because that poly will revert to ortho, you might see your ortho level climb as it goes through the system, so your far point might have a slightly higher orthophosphate residual as that poly reverts to ortho. There are online orthophosphate monitors out there that you can purchase. You can have them at your plant or a pump station and basically get continuous readings every 6 minutes of your orthophosphate content. I mentioned in that first study doing coupon testing, and that's based on the NACE protocol. What you're really going to look at is, like you saw in that study, is look at finished water without your corrosion control treatment, and then with different types of corrosion treatment. So you could look at pH adjustment, you can look at different types of phosphate products, and what you ideally want to do is run all those coupons in the same water quality during the same time period. And typically you'll run them approximately every 90 days. What you should focus on is the trend of data. So when you make a corrosion control change, does the corrosion rate go down on those coupons? The corrosion coupon rack is pretty simple. It's a PVC rack, typically 3 positions where you'll put a mild steel, a lead, and a copper coupon in it. You can have adjustable flow rates anywhere from 1/2 gallon per minute to 3 gallons per minute. But like I said, you'll do multiple locations. So one before corrosion control treatment, and then a couple after your corrosion control treatment. In this case, a system was looking at corrosion control coupons and making different changes over time. You can see from 2002 to 2010, they were doing this monitoring program with the coupons. And in this case, you're looking at the lead coupons. As they made treatment changes, you can see that they had less variability in their coupon rates, spiking and going down. And the corrosion rate over time was going down as they changed their treatment options. So it's a way for you to monitor your process and what's going on with it long term. If you also physically want to look at the coupons, these are from a different system, but this is what the mild steel coupon looks like, where you see a high corrosion rate on the coupon. And with a 50-50 treatment, with a 50-50 polyortho blend, you can see that you can still read the corrosion coupon number on it. So you can just physically see that the mild steel didn't corrode as much when you're feeding a blended phosphate in this system. So this can give you an idea, and you can run this for pH. You could run this for alkalinity or other parameters in your system to see how they're affecting your corrosion rates if you're going to make modifications to your corrosion control treatment. So in summary, phosphate use is extensive in the US. Very large systems use phosphate, like the city of Chicago, the city of New York, Milwaukee will use phosphate products. And very small systems, so small groundwater plants that might only treat 10,000 gallons a day might use a phosphate product as well. The idea is both types of systems are feeding it to get a benefit, whether it's getting into compliance with the lead and copper rule, or it's providing clean, clear water, so you're sequestering iron and manganese, so you don't have discolored water in the system. It may be something as the system wants to reduce their flushing time so they don't have to flush fire hydrants for 30 minutes to clear the water off. You might also see a reduced disinfectant demand as you clean up some of that scale and tuberculation in the system. The idea with the phosphate product is you're doing a product and a dosage to get overall better water quality for your end use customer, so they're not calling you in the middle of the night or all the time to complain about their water not meeting their expectation. Thank you.
Okay, thank you, Darren. Good information. Thank you everyone for attending today. We do have a few questions that came in. The first one, Darren, is can you define DIC?
So DIC is dissolved inorganic carbonate. It's a function of your total dissolved solids, your alkalinity, and your pH. What it truly is looking at is you'll do a DIC number. There's a couple different ways to express it. A lot of times you'll see it as DIC as C. What it really means is how conductive your water is. So as your DIC number goes up, your water wants to conduct a current, which means you'll be able to set up a corrosion cell easier. So typically in that case, if you have a high DIC number, you might have to go to a higher orthophosphate content level to get corrosion control in that situation. You might have to target a higher pH to get corrosion control. And in some cases with really high DICs, you might need to do both phosphate and pH adjustment in order to get corrosion control. So basically that DIC is trying to get your water to make your water corrosive with that corrosion cell. So you're fighting against it at the higher levels.
Okay, and are the rates mentioned here all dosage rates or are they ortho residuals?
So when we talk about dosage rates, you kind of got a couple things you're looking at. So when you're dosing at an orthophosphate target of 2, your residual should be pretty close to that 2 milligrams per liter in the system. In the one case study, we talked about a target of 3.2 as total. Remember, part of that was as poly and only part of it is ortho, 85%. But once you start feeding, you'll initially not see that total orthophosphate content in the system, so it'll be lower as that film starts to establish itself. That's called the passivation period. Eventually, what should happen is once you get that film established, your dose at the plant, if it's 1 part or say 2 parts is ortho, you should see that pretty consistently at that high level throughout the system. If the ortho is dropping out, there could be a couple different things going on. If the ortho level, say, drops from 1 to a half a part, it could be precipitating out with hardness, so you're not getting it in the system. It could be a biofilm is consuming it. So one of the things you might check there is, do I have disinfectant residual? Because I need to have monochloramine or free chlorine residual in order to keep that bacteria from consuming the phosphate content. So if you see a residual drop in the system versus your dose, then you might want to look at some things in the system to make sure that the numbers are getting closer together. So it's definitely something to keep an eye on.
Okay, and will an ortho or blend affect any changes in finished water as far as taste, pH, etc.?
So typically we're not feeding much of an orthophosphate or a blended poly ortho to the water to affect pH. Now there are some waters, if you're super low hardness and alkalinity, so you get under 10, if you feed one of the low pH products like a zinc ortho or a phosphoric acid that has a pH less than 1, you might then notice a slight pH effect. If you've got any kind of hardness or alkalinity though, because we're only adding 1 to 3 milligrams per liter, you typically won't see any change in pH. I've had consumers over the last 20 years at Carus that when we've added a phosphate product and the water plant told the community that they added it, some customers would claim they could taste it. It's rare that I've heard that, but it has come up a few times over the years. I don't believe you can taste it. It's at such a low level that I don't see much apparent taste to it, or other coworkers that I've worked with. But we have had some customers that claim they can taste it even at 1 part per million or 2 parts per million in drinking water. But I think that's a real rarity.
Okay. Thank you, Darren. Thanks for that presentation today, and thank you everyone for joining. Have a great day.